everyone. Welcome to another episode of CUDA Education. Today, we are continuing our journey of investigating the compute n body algorithm. And for those of you guys that don't know, we basically have a um, application that has a bunch of particles and it does all this stuff. But what we focus on this particular series is creating a new set of particles in the corner that's independent of these particles, that basically is rendered and created via a new set of pipelines, and also it's moving around. So it's moving around independently, not anything to do with this, but it's moving around independently in the corner. And we have to do graphic stuff, we have to do pipeline stuff. We have to do graphic stuff, we have to do compute stuff, and of course we're creating a new set of pipelines that is independent of this main application here. So that is the task at hand for this video. This is part two of this series. So um I already did a first already did a first discussion with it, basically starting all the way from here, going down to here. Okay? So all of this stuff here we've already covered, right? And we're now, all of this stuff we've sort of discussed, and we're now interested in. Come on, go back down. All right, you don't want to go back down. It's fine. And now we're interested in. Where are you? We are interested in everything down here, going down. Okay. A couple of things that I want to clarify before we start on the new section. So this is everything going down, all the way down to here, right? We still have more stuff to go after we finish here, but there's still more processing to be done. But for today, we're just gonna end right here. But there's some things I want to clarify from the previous video. The main thing that I want to clarify is that when we initially run the program, right? So when we initially run the program, uh, we we move data over from CPU to GPU, right? So in the previous episode, we talked about having to move data from CPU to GPU because, alas, all of this stuff, all of the source code stuff, for the most part, is it's on the CPU, right? Um, but what happens is that what was a sort of a point of contention for me was that uh, on the initial start of the application, there has to be an initial position and velocity calculated for these particles, right? So remember now, we're gonna have a set of brand new particles over here, but on the very first initial run or setup of it, those positions and velocities is going to come from the CPU. Just the initial position and velocity is going to come from the CPU. After things have been moved over, to the GPU, then the compute shader on the GPU side, takes care of updating the positions and the velocities and stuff. But we have a calculate initial positions and velocities, right? So all of this stuff is CPU side, and then we move the data from CPU to GPU, but the initial positions and velocities is done on the CPU. Okay, so that was my kind of confusion because up here we talk about the compute shader can read and write and update positions and velocities of the particles, right? But the thing is that this only happens after the application gets going, after we have that initial calculation and everything is pushed over to the GPU and the GPU runs with it, right? So the initial calculation is done on the CPU side, right? And then after that, everything else is done on the GPU side via the compute shader. So I just wanted to clarify that up because it was something that was worrying me. I was like, did I communicate this thing wrong? Did I say something? But it's actually, I was kind of both right, but it's just that the initial calculation is done on the CPU, then it's moved over to GPU, and then the GPU can can deal with updating positions and velocities and everything going forward, right? So that's one thing I wanted to just clarify. Another thing that I want to just do from the get go before we get into part two is that I didn't realize this, but in the application, you actually have the ability to pause, right? So you have the ability to basically, pause, you know, basically how the particles move and all of that stuff, right? And you actually can do it by pressing P. Okay, so you press P, and then you can press P again to basically get the particles moving again, right? So pause, P pauses, and P unpauses, right? It's the same, it's just a toggle. This is going to come up later when we start dealing with part two. So here I have this wind merge situation going on where basically I am basically, I have the original file here, and then I have, my updated file here where I have, I have my moving particles and stuff, but I'm not going to show you guys, the final result until the very end, right? Because I, have to make sure that you guys, you know, walk through the process with me before I actually show you the result, right? So, um, yeah, that is that. So we so right we right so we I have this win merge situation here where I have the two files and we're just kind of seeing what are the changes and the updates. We went through it the last episode, and then we're basically down to here. Okay, so we've done all that needs to be done, and we're here. Just as a big picture, thing. All the things in orange is sort of added code, right? So I know we're doing something that you might consider trivial, but Vulkan being Vulkan, we have to be explicit about everything. So this is all of the additional code that we have to create a new pipeline, an independent pipeline that has um, that's in the corner with independent particles that's not affected by the main particles, and we have the particles moving, so there's computation that needs to be done, not just graphical stuff. So this is all of the things that we have to tackle with this example. The default application, what I've been running so far in this video is yeah, the default application is available on GitHub and all of that stuff. I have the link down below for the default application. This here I'm butchering and modifying the code to basically do what I want it to do. But we're gonna now continue through the process of investigating. So we last thing we did is we dealt with the fences and semaphores, CPU to GPU synchronization, and semaphores GPU synchronization. And now what we have to do is we have to build a corner compute command buffer, right? So we have to basically tell the GPU, hey, we're giving you instructions on how to proceed in order to give us particles in the corner that are moving, and that's what we're doing. So we build corner compute command buffer, right? Which is this thing right here. um, build corner compute command buffer, and then we have a bunch of stuff that's going on. The first thing is we basically begin recording the command buffer. We bind the pipeline, bind the descriptor sets, and make the delta time data via push constants available to the compute shader during command buffer runtime. So, um, I don't want to get into bog you down with too much details here, but we bind the pipeline, right? And it's this corner particles dot corner compute pipeline. We bind the pipeline, we bind the descriptor set, right? So the descriptor set layout and everything, corner compute pipeline layout, all of that stuff. Bind the descriptor set here, right? So bind the pipeline, bind the descriptor set, and then we calculate our delta time. Now, this is where the pause comes in. So if it's paused, we basically freeze everything. So everything is at 0, 0, nothing gets updated. Position velocities, nothing gets updated. Everything is at 0, 0. And if not, we set delta time to frame time. Now, frame timer is a variable that is it's sort of like it's a CPU side variable. It's not necessarily Vulkan or anything, but it's available to us basically with the header files and the other files that are associated with the application. We have this frame timer variable that lets the GPU know what the clock is and all that stuff, right? So we have that there. Um, Make the delta time data via push constants available to the compute shader during command buffer runtime. So remember, guys, we are inside of the command buffer because we've started recording. VK command buffer begin info. So we've started recording, right? So now we have this VK CMD push constants command. That's what we're doing is we're trying to basically push the data, the delta time data, from the CPU to the GPU. Now we have to do this fast, quickly, and it's on a per frame basis. So this is extremely fast. This is all happening on a per frame basis. So guys, when we play around with 110, 122 frames per second, understand that this stuff has to happen really, really fast. Now, in order for it to happen really fast, we have to use we have to use push constants as a go-to means of doing that, but only if the data needed to transfer is small. So this is a quick and fast per frame transfer of data from CPU to GPU. So the CPU needs to communicate to the GPU clock information, time information, extremely fast on a per frame basis, right? So um, push constants is the method of choice for this. It's very quick. It's very efficient. You're not dealing with buffers. You're not dealing with descriptor sets. You're not dealing with staging buffers. You're not dealing with any kind of cumbersome transfer. Basically, what it's saying is, you know, make the delta time data via push constants available to the compute shader during command buffer runtime. So, you know, remember we're still in the command buffer, but we're saying, okay, make this delta time variable information from the CPU available to the compute shader during runtime. Notice that the call here, corner compute layout, the VKCMD push constants, notice that it references the stage that it's supposed to be available. VK shader stage compute bit. So that basically means the compute shader has access to this information. Okay, so that's what that is. Now we get into the land of threads and groups. So we have a bunch of these particles, right? I know I'm using the default application as a reference, but we have a bunch of these particles, and they need to be processed and dealt with on the GPU side, right? But we're not, it's not like you just throw these particles on the GPU and the GPU knows what it has to do. it has to be done in an organized fashion. Okay, these things have to be done in an organized fashion. So what happens is that welcome to the land of threads and groups. So threads, each thread sort of represents a particle, and we group these particles into groups, right? So to manage the whole process and do it in an organized fashion, we group these threads or these particles into groups, and then we try and figure out how many groups do we need in order to process all of these particles, or how to process all of these threads. um, I actually forgot to investigate this, and I need to investigate it. You know this particular, the way how it's done here is that it's done with 200. It associates 256 particles with a particular group. I'm not sure necessarily why 256 was used, but I do know from my NVIDIA CUDA days that we have streaming multiprocessors, we have warps and all these things, and sort of the GPU likes to do things in multiples of, what is it, 32 or something. Um, so anyway, I mean, I didn't fully investigate this 256, but basically, we have groups, and then the groups represent sort of a batch of work, and that batch of work is submitted to the GPU. GPU does what it needs to do, and it's sort of more efficient than just like giving it a big blob, right? You break it up into groups, and we have groups of 200, and each group is 256 particles. Okay, now the thing is that interdivision only cares about the whole number result. So when we get back here, one thread per particle, right? So one thread per particle, we have a group of 256, and then we have this math here to calculate the groups. Okay, now it's very important why we do it this way. So our corner particles that count is the number of particles that we have that we want to actually process, right? We need to deal with these number of particles. Okay, but we need to break down these number of particles into groups of 256. Okay, but the problem with division here, right, is that you have to be careful, because when you do this division, integer division sort of only deals with the integers, right? So it doesn't care about 1.5 or 1.4 or 1.3 or whatever. It just cares about 1. Or if the result is 2.2 or 2.5 or 2.8, it just cares about 2. It don't care about the point whatever that happens after that. As far as it's concerned, it's point 0, right? So in order to get around that, we have to basically do a roundup trick, and that roundup trick is this piece right here, which basically just increases the numerator, so that whatever number of particles you have, you sort of make sure that the result in terms of the division, the whole number result can accommodate all of the particles that you have. Okay, so uh so that's what the number of, that's how we calculate the number of groups. And actually here I sort of break it down for you a little bit. So beware, integer division only cares about the whole number result. So you make sure enough groups are created to cover all particles by adding an extra 255 particles, right? And that makes sense because local size is 256 minus 1, that's 255, right? 255 particles plus local size minus 1. We'll call it the roundup trick. Okay, so example 1, without roundup. Let's say we had 257 particles. So we have one extra particle that is outside, that is one extra outside of our 256 group. So we have 257 257 divided by 256 equals one group. Remember, we only care about the whole number. We only care about the first digit. So one group is one group created, which is wrong. And that's going to be wrong because that one group is only 256. So literally, literally, you are negating you are negating that other particle. So it doesn't have to be just one particle. It could be like 10 or 20 particles or 30 or 40 particles, right? As long as you have the one as the whole number, that's what integer division sees. So it's wrong. That one group can't cover your 257 particles. So in order to deal with that, example 2 with roundup trick, 257 particles again, we have 257 plus 255 divided by 256, right? Which is the number of groups that we have the number of particles per group. And we get two groups created, right? Those two groups can cover the 257 particles, okay? But then you ask, okay, but you have two groups, so now you know, you have extra threads, right? You have what happens to those extra threads when when you when you create two groups, which is 500 plus, you're going to have these extra threads in that other extra group, right? Because only one thread is actually going to be doing work. What do you do with the extra threads? Well, actually, what happens is that in our shader logic, um, we have this thing right here. Okay, we have this logic right here. So it says, we're not going to get into the mechanics of it, but basically, each if I is a particle, right? A particle index, like the index of a particle. If I is greater than or equal to the total number of particles that we've received, then we immediately return. So this logic here prevents us from trying to process stuff that's non-existent. So on that 257th particle, in group 2, we're going to process that first particle because um like, yeah, well, greater than or equal to, but we're going to process that 257th particle. But then after that, for every other quote unquote particle that we or thread that we have in group 2, we're just going to return. We're not going to do all of this processing because it's non-existent, right? So that's the logic of this um, so, well, what happens to the additional threads created? 2 times 256 is 512 threads, but I only have 257 particles. Logic in the compute shader takes care of that. If I is greater than or equal to p length, return. Basically, if you try to process more than the number of particles you have, you just return immediately. So you don't process more than what you have. Now, the greater than or equal to, I know people might say, well, yeah, but you said equal to, so the 257th would be equal to whatever. But I think, don't quote me on this, but I think one starts counting from zero and the other starts counting from one. So, uh, um, one is going to be 250. The 256th one is actually the 257th one, and that means it would the very last particle would pass and blah blah blah, and it will actually process. But let's not get bogged out in semantics. You guys get the point, right? So basically, we would process all of these things, and we'll process all of the particles. And as we said, we made sure that the number of groups that we're dealing with is lined up properly. Okay, so that is that for this. So group 0 handles indices 0 to 255, right? Group 1 handles 256 to 512. So see, this is exactly what I was talking about. The very first item in group 1 is actually number 256, right? So 256 is not greater than or equal to 257, right? So number 2, so ID 257 now is going to be greater than or equal to 257. So then it fails and then you return. Okay. So anyway, group 0 is 0 to 255. Group 1 is 256 to 511. Group 2 is 512 to 767, etc., etc., right? So that's our logic here. Now what we have to deal with is we have to deal with, so that's this guy right here, and it's actually not too bad, right? So we do VKCMD dispatch, and now we're dispatching. We have our groups and all that stuff. Maybe we'll get into the parameters for this stuff once we start running the code and all that, right? But basically this is us doing, you know we're actually doing the work now of the particles, right? So we're making sure that the particles get to the GPU, and the appropriate stuff is done on the GPU for these particles, right? And we group them up together, and we send it over to the GPU, and then the compute shader the compute shader can do its thing, um, which we'll get into more another time, right? Um, and then now what we have to deal with is pipeline barriers, right? So we have to deal with pipeline barriers, and then we'll be done for today. So barrier compute writes, then vertex input reads within the same frame. So what happens here is that welcome to the land of pipeline barriers. We have to make sure that when the compute shader writes to the buffer, aka it's updating speed, it's updating velocity, that the graphics pipeline isn't trying to read from the buffer. So, isn't trying to read from the buffer. So it can get the vertex data to draw and then present to the screen. And what this is called is a vertex fetch, right? The vertex fetch. So we got to make sure that while the compute shader is writing and updating information in the buffer, that we're not doing a vertex fetch, right? We're not doing a vertex fetch, because remember, the graphics, we got to present to the screen, right, guys? You guys get all fussy and stuff if you run your application and you don't see anything on the screen. So you want to see stuff on the screen. Well, if you want to see stuff on the screen, we're gonna have to fetch the updated vertex information and present to the screen. But we have to make sure that the compute and the graphic stuff isn't clashing with each other and competing, and we also have to make sure that um, the API, the application, Vulkan itself isn't holding data inside of a cache and not releasing it for the graphics pipeline to see it. So these are battles that we have to fight, which is why we have this pipeline barrier conversation, right? So we have to deal with all of that. This all happens within the same frame, right? So you can understand the time crunch that these processes are under, right? We have to do all this stuff. The compute has to update the stuff, the buffer. Graphics has to read the buffer, um, and present to the screen, and it all has to be done, all within the same frame in a very fast time. Remember, we're always talking about 120 frames per second. Okay, so you can imagine how fast, we have to build these frames. Okay, so you also need it for memory visibility. So like I just said, because of the update memory could sit in the update memory could sit in a cache and not be visible to the vertex fetch from the graphics pipeline. So the pipeline barrier forces visibility to all humankind and machine kind, right? So when I say this, what I mean is that, you know the API, the driver, the powers that be, everybody, the information is updated, but it's still sort of in a cache and it's not being released to the graphics pipeline, right? And the graphics pipeline can't see it. So what this pipeline barrier also does is it forces the updates to be visible to the graphics pipeline, so the graphics pipeline can actually see updated information. This specific VKCMD pipeline barrier guarantees two things for this buffer range: execution ordering. Don't let vertex input reads happen until after compute shader work reaches the barrier. So basically, you're not going to read until the graphics shader is finished doing its work, right? Memory visibility plus availability, memory dependency. Make sure the compute shader's writes to the buffer are available and visible to the vertex fetching. Okay, so again, like what I said, your the compute shader is writing stuff and updating stuff, but we have to make sure it's visible to the graphics side, to the vertex fetching. These are distinct concepts: ordering, when operations are allowed to occur; visibility, whether later stages actually see the updated bytes. And then we end our command buffer recording. All right. So that is the discussion for today. And we are not going to go any further with that stuff. Yeah, this didn't line up properly. It's supposed to be a transparent hole too. But anyway, all right. But that's it, guys. That's it. So we have made some progress on our journey. So in due time we'll get to see the final result. But I think we have done a lot of the heavy lifting already. I know it's a lot of code. I know it's a lot of moving parts just to have another set of particles in the corner moving around, independent. We're not syncing with the main application or anything. Even though, it's only one GPU I do have on my system. So, there is some implicit synchronization because I only got one GPU. It's not like I'm generating these particles with a second GPU on my system. I just have one GPU. All right, guys, but this is this is good stuff. This is good stuff. We got through a lot of stuff, and I think everything flowed a little bit better today because I'm a little bit more comfortable. I got to clear up some stuff in my head, and we're well on our way. So I have to finish. Just so you guys know, we're basically ended here, right? So if we go start from the top, all the things in orange is added or modified things. Um, we are basically here, and then we have to do prepare corner pipeline, and then everything else is not too bad after that, right? It's just minor stuff. Um, yeah, it's not too bad. Well, yeah, we do have something to do though, but yeah. So we have our work cut out for us, but I think we've made good progress and we've done a lot of the heavy lifting. So this is where we're at, guys. This is CUDA Education. Remember, guys, if you want to be able to participate in all of this stuff, you need to get tutorial number 1, which is the installing the Vulkan SDK on your Windows-based machine. Um, Basically, you have to make sure you have a Vulkan-capable GPU on your machine. And then tutorial number 13 is installing a lot of these examples. Now I'm taking a baseline example. From from the author, basically, and then I'm modifying it to do some other stuff. But you want to you want to be able to run the baseline example and all of the Vulkan examples on your machine, and then you could sort of follow along from there. um, so that's tutorial number 13. It gives you a bunch of examples that you should be able to run. I assume a Windows based machine with a Vulkan capable GPU. The example set does have the example set does have ray tracing algorithms on it. If you want to be able to run those ray tracing algorithms, those are ray tracing applications, you're gonna have to get a ray tracing capable GPU. Now, the thing is that in these modern times, because we are now in 2026, um, a lot of the computers that you get with their integrated graphics card. So it's not even a discrete graphics card like an Nvidia or an AMD discrete graphics card, or what have you. It's integrated graphics card. The modern computers that you buy in 2026, a lot of them are able to run Vulkan on the integrated graphics card, right? So you don't necessarily need a machine that has NVIDIA discrete GPU on it, but make sure you do your investigations before you go out and buy a machine. Make sure whatever machine you're getting that you're able to run Vulkan on that machine. Okay. And this is Cool Education. You guys know what to do: like, subscribe, share. Be the leader in your community. If you know someone that's artistically inclined, that's creative, that's interested in this stuff, that wants to, prepare themselves for the future, definitely start getting your hands dirty in this stuff. Everything is going digital. Um, and the world is changing as we speak. Thank you for watching. This is Good Education. Have a great day.